Hello everyone. So in the last video we discussed how to pre-process our reviews and how to use that process reviews to create our bag of words model. So if you haven't checked out that video, go check it out so that you are able to understand what we'll be doing next. So in this video we'll be learning about support vector machines and how they work and what is the intuition behind them. So let's suppose we are given a classification task and we are given a data set, and the data set has namely two features x1 and x2. So we can easily plot them on a 2D graph, 2D space. Okay, so now the task falls upon us key we have to classify, we have to draw a decision boundary in such a way that if any new future data comes in, we're able to classify them. Yeah, okay, this is red or this is green. So like I have to draw my decision boundary in such a way such that it does not lead to overfitting or underfitting, like it is generalized. So for those of you who are not aware what is underfitting and overfitting, so overfitting is basically like my decision boundary, whatever classifier that I've made or the decision boundary that I've defined is able to classify my the data that is already known to me. Okay, let's suppose this is the transition boundary and it is nicely able to classify, yeah, this is red, this is green. But let's suppose some new data comes in and it is not working great on the new data, basically my test data, so it's overfitting. And underfitting is basically I draw a line in such a way that it is not even able to classify the data that is known to me. Let's suppose I draw a line here, this is a line, okay, and is not able to classify whether the new data, like with two features like x1 and x2, is either red or green. So here the SVM comes into play. Using SVM we are able to find the best decision boundary and which is generalized and does not lead to overfitting or underfitting. So in this we draw decision boundary in such a way we make use of the support vectors. Like these are the vectors which are closest to this decision boundary, and we make use of the support vectors and we draw a decision boundary in such a way that it is at a maximum and equal distance from both of these support vectors. So this maximum, this line or hyperplane as we call it, is called a maximum margin hyperplane, and it is actually at a equal and maximum distance from both of these support vectors. So the reason behind this is called a hyperplane or not a line, because it depends on the data set. Right now we have a 2D space, we can represent it in a 2D, we have two features and we can represent it in the form of a 2D space, hence it's looking like a line to us. But let's say there are three features, and that is x3, which is the z coordinate, which will be coming out of the screen. We need to draw something called a plane which has x, y, z coordinates, and we'll draw a plane to classify between the classes. Okay, let's suppose we have four features. We can't visualize or plot a graph of it, right? Because we are we are aware only of the 3D world. There are like basically three coordinates in the coordinate system, x, y, z. We can't imagine four coordinates, right? Four-dimensional geometry. So in that case we use the term hyperplane so that it's general. And I'll explain you with an example. Let's suppose I'm given a task of classifying apples and oranges. Okay, so let's suppose this is apple because this is red, and let's suppose this is green orange. Okay, I'm just joking. Orange color oranges. And see, this particular apple has very distinctive features like x1 x2. This perfectly looks like an apple, and this orange has two features, x1 x2, and they are very different, right? This perfectly looks like an orange, but let's talk about this apple and this orange. The features of this apple and this orange are somewhat similar, right? Because yeah, they are not actually, the features are not equal, but they are somewhat similar. So these are my support vectors. Yeah, like the features of this apple and this orange are similar, but still, yeah, there is a fine line of difference between them. There's a fine line of difference between their features. So I can use that fine line of difference to draw my decision boundary, so that it is equidistant from these vectors and at a maximum distance from these vectors. So yeah, SVM works great for linearly separable data. My linearly separable data is basically if I draw a line or a hyperplane or a plane, so I'm able to separate them linearly. But how can I find support vectors here and draw a line and just be able to classify them? I can't do that, right? Like I'll have to draw a circular decision boundary. Like I'll have to draw a circle so that whatever comes inside the circle will be green, whatever comes inside the outside the circle is red. So I can't do that with SVM directly. So what I'll do is, let's take an example. Let's take an example that we have a data set which has only one feature. So since it has one feature, I can plot it into a 1D line. Okay, so these are my points, these are my green points, these are my red points. So right now, I can't just draw a line and classify them. So what I'll do, let's tweak the data and subtract 5 from all of my data points. So they'll move towards left by 5 units. So this green group moves closer to 0. This red group moves beyond 0. Okay, so now what I do, whatever result that I'm getting out after subtracting 5, I'll square it, and that will basically my mapping function. F equal to x minus 5 whole square is my mapping function, and whatever the result of my mapping function is, that is my extra dimension. So what we do is, like, we map our 1D data into 2 dimensions. So whatever the result of this data is coming, let's say I'm taking this particular feature, this particular green feature, it has some x value. Okay, let's say it's 6. Okay, so 6 minus 5 is 1 whole square is 1, so the y value will be 1. So it's plotted, let's say this is the 1. Okay, so I add an extra dimension by doing some by finding some mapping function which takes in the features as the argument, and it acts as an extra dimension. So this f is equivalent to y, the y coordinate. So it might be like, you might be aware, this is the equation of a parabola and upward parabola. So I took a feature and I inserted it into my mapping function and find out the value of my extra dimension, or the extra coordinate, that is my y coordinate. So basically I map into a higher dimension, and now you can see I am able to linearly separate the data. Like, whatever to the positive of this line is red, whatever to the negative of this line is green. Okay, so let's take another example where we already have 2 features. We are already in a 2D space. Okay, so what we'll do is compute some mapping function, and whatever the result of the mapping function, that will be the value of our z coordinate or our extra dimension. So in this way, in the last example, we moved from 1 dimension to 2 dimension. In this example, we will move from 2D to 3D, so 2D to 3D transformation. So using the mapping function, which basically takes my 2 features and returns some value which will be my 3rd dimension, I'm able to plot this in a 3D space. So basically the z coordinate, z is basically the result of my mapping function. Now I'm using a hyperplane, or since we are in a 3D space, I would like to call it a plane. Using a plane, we can easily classify whatever to the positive of this plane is green, whatever to the negative of this plane is red. So let's say if a new data comes in, I'll put it into my mapping function, the features of my new data, and calculate the z coordinate and map it to a higher dimension. And whatever the location is, like if the z is less than this plane, okay, so if it's below this plane, then it will be red. So yeah, this mapping function and this the concept of mapping the data into higher dimension works for less dimensions, like if you have 2 features or 3 features. But let's consider there are 49 features, and from 49 feature I'm putting all my 49 features into, first of all, computing a mapping function which is able to, like, keep computing a mapping function for 49 dimensions is very computationally expensive. And after that, like, putting all the features, 49 features, and finding that 50 dimension, and then finding that SVM on that 50 dimensions is very, very computationally expensive. So we avoid using this mapping function, and we use something called Kernel SVM. So in Kernel SVM, we avoid mapping the data into higher dimension. We do all our calculation in the original dimension, and still we are able to find the decision boundary effectively. Okay, so I'll explain how this freaky looking equation translates into this graph. So this basically, consider this x1 as x2. Basically, these are my features. In this dark blue is this xy plane, is basically like my points in my data set, okay, with x1 and x2 features. So let's say I take a feature x, and this is a landmark. This is red point in the middle of this graph is the landmark. So here I'm taking e to the power minus negative of vector distance, the square of vector distance between x and L. So let's take this as my x. Let's suppose this is x, which has some features x1 and x2, okay, and basically I find the difference between vector distance between these two vectors L and x, and let's suppose for some sigma it's quite big. So this whole exponent will be big, and since there is a negative, 1 upon e to the power something big will be, like, if not 0, it will be close to 0, right? We can see that z coordinate or the k is 0. So basically, like, we are not mapping it to a higher dimension, we are just calculating this extra coordinate, okay? We're just calculating, we're not mapping the actual data sets into a higher dimension, right? We're just calculating the k value or the z coordinate for this particular data set. So yeah, it's 0. So yeah, the k z coordinate of this particular point is 0, or the k is 0, so the z coordinate is 0. This is my xy plane, this is the z. So now let us talk about the landmark. What is if I put landmark in place of my x? So landmark, the vector distance between landmark and landmark is 0, because it's obviously the same vector. So e to the power 0 is 1. So at this point I get the k value or this z coordinate at this point, that this data set, as 1. So we can see 1. And let's take an example of this green point. It is somewhat close to the landmark. So this for some sigma, constant sigma, this is a small value, okay? So 1 upon e to the power something small will not be 0, but somewhat greater than 0, like let's say 0.2. So at this point I get the z coordinate as 0.2. At this data set I get the point as 0.2. okay, so you are getting the gist, right? Like, if we move away from the landmark for some constant sigma, while the sigma is constant, okay, as we move away from the landmark, this k decreases. So basically the z coordinate decreases, and this whole peak converges to the base gradually. So what is the role of the sigma here? The role of the sigma is basically like it's controlling the circumference of the circle. Let's say for some sigma I was getting this point, the k value or the z coordinate of this as 0, okay, for some sigma. But now if I increase the sigma, this is x minus L is constant because the vectors are not changing. As of now, this x, basically this red point is this x, for example, and this is coming out to be 0. But now what I do is like I increase this, so this whole value will decrease because this is constant. This I'll increase this whole value will decrease, and 1 upon e to the power something decreased. If the original was 0, 1 upon e to the power something was 0, and 1 upon e to the power something reduced will be greater than 0 na? Similarly for this point, if I increase the sigma, the circumference will increase. Like if I'm getting 0 for this, if for some sigma, for some original sigma I was getting 0 for this, but now I have increased the sigma, I will not be getting 0, I'll be getting, let's say, 0.2. So the circumference will have to increase to accommodate that change, right? Similarly, if I decrease it, let's say for this particular point I'm getting 0.2. okay, now if I decrease it, this whole value will increase. Okay, so 1 upon e to the power something increased will be less than 0.2 now. If I was getting 0.2 for some 1 upon e to the power something, 1 upon e to the power something will be less than 0.2. so the circumference will decrease. It will, let's say, it will be 0.01 or 0.1. so the circumference will decrease. So the circumference is directly proportional to sigma. Increase the sigma, circumference will increase. Reduce the sigma, circumference will reduce. Okay, so now let us talk about how we can use this property of this. Like if I regulate the sigma, this like if I regulate the sigma, the circumference will change. How can I use this property in my classification task? So let's suppose all the points which are coming inside my circle, this is the circumference, will be labeled as green. All the points that are coming outside will be labeled as red. So this is basically the circumference. So I have calculated my value in such a way, like I calculate the distance between this x. This is basically this is the x vector, which has features x1 and x2, and this is my landmark. So if I calculate this distance is small, and this distance is small, and the sigma is small. Okay, so 1 upon e to the power something normal is not 0, it will be greater than 0. Okay, so if the k value, if the k for this x and this L is greater than 0, then this is inside the circle, and let's say if this is the x and the distance between this and this is big, and 1 upon e to the power something big will be 0. So I have calculated my sigma in such a way so that it is at a perfect fit, and it is keeping the k value of the outer points which are labeled as red to 0. So let us move to our whiteboard. So suppose during the training of my classifier, I got a sigma which is 9, and it's not performing. It's drawing a decision boundary which is very poor. So let's suppose at some point of our training, the classifier draws a decision boundary something like this. And here, as we can see, there are some red points included in our decision boundary as well. So let us assume the landmark is here, and let us take this data point as our x. So distance, the sigma is 9 and huge. Okay, so I have some distance which is very large. Distance is very large. Okay, distance is large, and the sigma is also large. Okay, so the numerator is large, the denominator is large, so this number will not be very large, and hence this number will not be very large. It will be something normal, and hence it will not be equal to 0. If it were large, if this was a large number, then it would be similar to 0 or equal to 0, but this is greater than 0. So I'll get a k value for this point as greater than 0 and not 0, but I'll see that this point is labeled as 0, and I'm not getting a k value for this point as 0, and I'm getting something greater than 0. And similarly for this point, I'll look the distance is large, the sigma is large, but still I'm not getting the k value is 0. So what I'll do, I'll look at all those points, this point, this point, this point, and what the classifier will do is basically reduce the value of sigma. Okay, so after reducing, again it will draw a decision boundary, something like this. Okay, still I can see it is including some red points or 0 points, 0 data points in our class, in our decision boundary. So now again the sigma is somewhat smaller, but it is still large. Okay, so again this x, let's take this point as the x, so this will be a large number and this will be a large number. So and 1 upon e to the power something normal is still greater than 0. So I'm again getting a value of a k value for this data point greater than 0, and similarly for this the k value is greater than 0, k value greater than 0, k value greater than 0, k value greater than 0. So it will come to a conclusion that yeah, I need to reduce my sigma, the value of my sigma, by some more some factor. So now it will basically reduce the sigma and draw this decision boundary, which will perfectly fit our data set. It will be able to perfectly classify a data set, because for this point, let's say this point, the distance is small. Okay, the distance is small and the sigma is also small, so this is normal value and it is greater than 0. Okay, but for, let's say for this value, let's say this is our x, this is our x, and for this, like I'm getting something 1 upon e to the power some large distance and some small sigma, and I'm squaring it. Okay, so large distance, small sigma, small denominator, large numerator, so it will be a very huge value, and it will be somewhat similar to 0. Okay, so I'm getting a k value for this data point as 0, because it is outside my decision boundary. So whenever a new data comes in, I'll be able to classify it by regulating my value of sigma. So basically it has learned a value of sigma in such a way that any new data point that comes in and it is similar, it is outside my decision boundary, it will label it as red, and if it is less than, if it is inside my decision boundary or my circumference, it will label it as green. So let's suppose we have a data set something looking like this, and in order to classify my classes, I'll have to draw a decision boundary like this, something looking like a dumbbell. So basically what we'll do is take two kernels. As you can see, there are two landmarks, L1 and L2. So basically these are two different kernels with two different values of sigma, that is sigma 1, sigma 2. So for any red point, the k value of this kernel and the k value of this kernel, the sum of the k values of this kernel and sum of the k value of this kernel will be equal to 0, right? And similarly for a green point, the value will be greater than 0. So if let's suppose if there were some more green classes, you would have taken 3 or 4 or even 4 kernels. So that depends on our use case or our data set. So we have some metrics for evaluating our model performances. So we draw a confusion matrix in which, like, we are at this point, our classifier has been trained, and now we're evaluating the performance of our model. So one of the metrics is confusion matrix, and here in this it's a 2x2 matrix. In this, first we have the predicted, like the values predicted by our model, and these are the actual values that are known to us, that are known from our data set. So if my predicted value is 1 and my actual value is 1, so it is true positive. And if my predicted value is 0 and my actual value is 0, then a true negative. Yeah, so these two points, my model has rightly predicted. But there are some points which are actually 0, but my model has predicted them as positive. they were actually 0 and we predicted them as positive, so they are false positives, and some are actually 1 or actually positive, but we have predicted them as negative, so we these are called false negatives. So the data sets that our model has rightly predicted are true positives and true negatives. So we calculate a score, accuracy score. So we take true positive and true negative in our data set, and basically take the length of the whole data set: true positive, true negative, false positive, false negative. And basically, like, for example, it comes out to a value between 0 to 1, and if it's greater than 0.85, which means 85% accuracy, it's a good model, it's a decent model. So here we have already defined our x and y. X is basically our features or the count vectors for each of our review, and y is basically our labels, either 1 or 0. So we cannot use all of our data set for training purposes. We need to keep some data set for testing purposes as well, so that we can check whether how the model is performing on new data. Because if I use all the data, it might be overfitting, and I'll not able to check whether it is overfitting or not. So I'll just copy paste some code here. So I'm basically importing this train test split from sklearn, and this will basically return a tuple which will contain x train, x test, y train, y test, and I've given the x, the features, and the label, the class, and test size, that is 20%. And if you want the same shuffling and same type of shuffling and splitting as mine, so that our results are same, our accuracy results are same, you should set it to 0. Now we'll define the classifier. Okay, so I'll import this classifier, which is SVC, from sklearn, and the kernel will be RBF kernel, the Gaussian RBF kernel. Again, set the random state as same as mine. And now we'll use the fit method to fit our x train and y train. Yeah, so x test and y test will be used for testing, and x train and y train will be used for training. Okay, so the reason we are not using transform is because we don't want to return anything, or we don't want to transform our x train or y train. We just want a classifier to calculate the weights and all the parameters and all from our x train and y train, and store them in our classifier state, the object state. The object is this classifier, and in the future, if any new data comes in, I'll able to use that weights to make the prediction whether the review is positive or negative. And there is no method called fit_transform in classical machine learning algorithms. So now we'll do the predictions, and first of all I'll run this code. So yeah, our x train and y train have been created. This is x train. Similarly, y train, y test. Yeah, so now we'll predict the results, and we'll do the prediction on the S data. There's a function called predict, and I'll pass on to my data. So the shape of this, the number of rows in X data will be same as the number of rows in my Y pred. Okay. So basically we have some Y test, basically which are some new data, actually not new, but yeah, according for the model it will be new. For us it will be old. For the model it will be new, and basically we'll compare this Y test with Y pred to see how the model is performing. So Y pred is basically a predicted data. As we saw in the confusion matrix, this predicted will be Y pred, and this y test will be the actual. Okay, so if the y pred match, if for example, if for the first test data, if the y pred matches with the y actual, then it will be either a true positive or true negative. It doesn't matches, it will be either a false positive or false negative. So I'll run this code. Now we have calculated this y pred. So basically for our test data, we have predicted some results. Now we'll start off with evaluating our model, that how good our model is performing. So from sklearn.matrix module, I'll import a class called confusion matrix. A function called confusion matrix, and I will pass the y test and y pred, which is actually y actual and y predicted. So based on that, it will be able to test whether, okay, here is 1, it's a true positive. Here is a 0, it's a true negative. Here it's a 1, okay, y test is 1, and at y pred is 0. So it's a false negative because it was actually 1 and we predicted as 0. And if here is a 0 and it is 1, we predict that as 1. So that's a false positive. So basically at 0, 0 we have false positive. In a two-dimensional matrix, at 0, 0 we have true positive, and at 1, 1 it's a true negative. So accuracy is basically true positive plus true negative on the length of the whole test data set. So basically sum of the whole, this sum 0, 0, 0, 1, 1 and CM0 and CM1 will basically give me an accuracy. I'll print the confusion matrix as well. This is my confusion matrix where 256 and 104 are my right results. Either they are true positive or true negative. I am not aware about the convention whether they actually take this first for this direction as actual, or this direction is predicted, or actually they take this as 0 or 1 or 0 or 1 like we have taken. So but that's for sure, either this is a true positive or a true negative, or either this is a false positive or false negative. So 104 plus 256 divided by the matrix, 104 plus 130 plus 33 plus 18 plus 256. So I'm getting this 87% accuracy. So which is fabulous accuracy given the size constraint of our data set, because in these type of models we require at least 5 to 10,000 of records or reviews. So we have achieved a 87% accuracy with just 2055 reviews. So you should applaud for yourself, and that's a great job. And stay tuned for more videos like this, and thank you.